Welcome everybody to Procedural in Motion. This afternoon is, we hope it'll be a very educational, informative session talking specifically about procedural workflows for motion graphics and advertising. We've got about 4 speaking sessions as well as an industry panel where we'll have some of the industry people discussing various topics in one of the sessions that starts at 3. The way it'll work, I think in general is, and maybe each speaker can decide how they want to handle this, but in general we should be kind of saving the Q&As until the end. We've got this catch box that we'll be throwing out, and what you do is catch it, and then you talk right into it. Talk right into the black circle so that we can make sure we capture your audio. Without further ado, I'd like to bring in the famous Entagma, Moritz and Manuel. Over to you.
Hello.
Hey, thanks, Chris, for the introduction. Thanks for the flattery. And good morning to you guys. Glad you made it to Procedural in Motion. Thanks to Side Effects for having us. Thanks for all you being here, albeit at least for our time a bit early. So, and this time we actually managed to figure out a title for our talk beforehand, which is a thing that's not too common for us. And we're going to be talking a bit about VEX in motion graphics. So the usual question, please raise your hand who never used Houdini. That's a good thing. 2? Okay. To be honest, this topic is most applicable if you've at least dabbled in Houdini a bit. We will try and make it understandable and digestible even if you've never used Houdini. And we hope you find some interesting bits and pieces here that you can adapt to your workflow. So this is what we'll be talking about today. We'll give a short introduction about who we are, what we do. We will try to convince you that VEX is the most awesome thing there is on this planet. We hope to do so by giving you a few examples that are a bit hypothetical and showing a few examples of how we used VEX in actual commercial productions. And as always, here's this disclaimer, and I'm sure you've already seen that. It's just be aware that you might run into misconceptions. So I'm always showing this here. This is a survivorship bias. It's a diagram of where a plane that made it back to base had been hit, or in general, where planes that made it back to base had been hit. And the question, as always, is where would you put armor? And clearly, your first instinct would be put armor here, 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 or here. And if you think about it, planes that had been hit in those areas here, they just didn't make it back to base. They fall out of your statistics. And this is, in truth, these are the places where you would put armor. So that's called survivorship bias. And my point is, don't assume that some of the things we'll be talking about here are necessarily what made some projects work or what made things that we do work. So think for yourself and see what parts of our workflow and parts of our tips and tricks you can adapt. And admittedly, this was getting old, so I was researching common misconceptions, other common misconceptions that there are and people have. And it turns out there is this list of common misconceptions on Wikipedia, where Wikipedia tries its best at dispersing common wrong beliefs that there are in mankind. For example, they say stuff like this: humans cannot catch warts from toads, clearly, because the bumps on a wart are not, the bumps on a toad are not warts. But there are some worrying bits and pieces in this list. For example, this one: infants can and in fact do feel pain, and Wikipedia even provides 2 citations for that. 2. Other stuff that's in there is that sharks can suffer from cancer. The claim was made up in the 90s to sell, weirdly enough, shark extract to people. The redhead gene is not becoming extinct, and I like the Wikipedia quote here: redheads will not die out unless everybody who carries the gene dies or fails to reproduce. Humans have actually more than 5 senses, so there's sight, smell, taste, touch, hearing. But for example, you have a sense of balance, you have a sense of pain, of body position, and of body temperature, for example. All in all, you have about 20 senses. And now it gets interesting. People do not use only 10% of their brains. While it's true that a given amount of neurons only fires at a certain period of time, it would be a really, really bad thing if all neurons fired at the same time. Which leads to another thing related to our topic, learning. All humans learn in fundamentally similar ways, which is really reassuring for guys like us who are trying to teach something or to convey something. So before we go into the actual learning phase, let's talk a bit about what we've been up to lately, and we have been busy. There have been a few projects for a sportswear company we've been struggling to finish and finishing, and of course, we suck at planning, so last week I had vacation, and I've been to Romania. Anyone here who has ever been to Romania, Romanian relatives, or who is from Romania, lift your hand. Oh, there's one guy, nice, two. Okay, so I didn't take this picture, this is from Wikipedia, but I think it's an image you still see on Romanian landscapes. And I've seen the Romanian landscapes. And here's the story. This is where I've been. It's in the backcountry of the backcountry, and here's my wife, and here's my mother-in-law. And they fled the country in '88, 1 year before local socialist leader Nicolae Ceausescu was driven out of office, to put it nicely. And after 30 years, they decided they wanted to reconnect with the country they came from. So they bought this tiny old house here, and they started to renovate it. So I've been to lots of Romanian stores, and weirdly enough, in Romanian department stores, you can buy stills, and those are man-high stills with a capacity of 100-liter outputs. And I'm not sure how the legal system works in Great Britain, but in Germany, this is surely illegal, and it's nothing you want to hand out just to people, to general people on the street. And I've also seen Romanian electrical installations while renovating the house. Which brings me to a section I'd like to shortly touch on, which is best practice. And it's not only if you're doing renovation or electrical work, but also if you're building setups in Houdini or if you're building programs using VEX. So this is the main fuse box of the house. And the electrician clearly put some notes behind each circuit breaker. And they go like this. So you have your main fuse, heating, lights, outlets for the hallways, for the bedrooms. And after I tried hooking up one light, I noticed that those were not the right fuses. So I kept investigating, and it turns out those fuses were also not right. So I found out these are the right fuses. The good thing is the main fuse works, and it's correctly labeled. The worrying thing is this one, which says lights for the bathroom, which work, and those two, which I just did not find. So what I want to say with this is document your darn stuff. Document your setups. If you're handing off setups to other artists coming in a project, to other freelancers coming into the project, try to make them understandable and readable, and try to keep the documentation up to date. So use color coding for different notes, what to do. Use notes, and try keeping them up to date when you hand over your projects. And also, if you're on the receiving end of this, if you're an artist coming into the project, test your darn things. This saved me from some shocks. And that's what you always do when you get a new setup. You just check out how this thing works, if it works at all, if it outputs the same thing that it was built for, if it might be missing in Houdini setups caches, if it might be missing 3D files coming into it. You just test the darn thing. Also, if you're building setups, and this is an image out of the hallway of this house, use standards. And I Googled electricity outlet standards, and electricity outlets are usually like 30 centimeters from the floor or from the ceiling. This sits at 1.60 meters, and it just slightly lifts this radiator here. We'll talk a bit about standards in VEX programming and stuff. It makes it easier to understand and easier to adapt if your setup uses certain standards that are standard either in your studio or within the whole industry. And also, do have a backup plan. I don't know if you know those stuff. This is a drywall dowel made by Fisher, and these are Wago electrical terminals. They are like the Logitech mouse or your Cherry keyboard of home renovation. They just work. They are kind of cheap-ish, and they do work. And I had to discuss about buying them, and I had to discuss every single thing. I brought 10 of those, and 12 of those. We used every single one. Have a backup plan if something does fail. And also, this is just some traveling advice. When you go abroad, when traveling, download Houdini before you start traveling. The EU made it easy to have your data roaming fixed in foreign countries, but still I had like a 1 gigabyte plan. I guess I'm gonna get a new contract now. This was after 3 days. I crossed 10 gigabytes after 5 days. Bring your stuff beforehand. And don't try rendering on your damn laptop. I will show you this image that I was rendering here. It took over an hour. It's just a 720p image. Laptop sounded like a jet engine. But to be honest, we never do that stuff either. So here is a view of my hip cottage-style co-working space. Yeah, the tablecloth is especially lovely. And I have a slight feeling that these might have been my last holidays at my in-laws for a longer time because they were hedging some weird feelings at this point towards me. But at least the light in the hallway works now. So let's talk a bit about what we actually do when we're not vacationing or finishing projects. And Entagma is this dude, that's Manuel, and this dude, that's Moritz. And we work at this small company in Munich called Sponsor, and we do 3D animation, CG work, VFX for commercial work mainly. We are 12 people, plus some freelancers, and this is our most current reel.
Your hands, my hands, your mouth, my mouth, your body, my body. Ooh, you make it all so simple. Oh, oh, so simple. You make it all so simple. Oh, oh, oh. I shake for you, baby. I shake for you, baby, all over. I shake for you, baby. I shake for you, baby, all over. You make it all so simple. Oh, oh, so simple. You make it all so simple. Yeah. I shake for you, baby. I shake for you, baby, all over. I shake for you, baby. I shake for you, baby, all over. I shake for you, baby. 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 I shake.
So that is what we do in our daily work. Thank you. Thanks, appreciate it. And by night we run this thing called Entagma, which of course you know, and we output a tutorial every 2 weeks concerning Houdini, and a stupid script we once wrote earlier this year described us like this. As a visual storyteller, Entagma, Vimeo's best channel, is the content production division of the 16-camera Google jump rig working on all 6 Bond actors. So, now that we got that out of the way, let's talk about this topic that we brought you, a topic that's very dear to us. And it all breaks down to this. When we work, we want to design intricate structures, intricate 3D work. And it is daunting, especially when you're new to a software or when you're learning a software while on a job or while on a project. And especially when that software is Houdini. And you're confronted with an interface that yields those reactions in you. It's a rather alien interface when you're coming from 3D applications or classic 3D applications. So it's a handful at first. So how do you approach this thing? Well, turns out Houdini has one thing that's really handy for you if you learn it. Houdini can be viewed as an operating system stringing together many individual apps. And those apps are called contexts. And here they are. They are contexts for animation, for compositing, image manipulation, for material design, textures, shaders, for geometry and volumetrics, for rendering, again for shading, that's deprecated now, and for programming, for VEX. So what we usually do at this point is we recommend people to start out with the geometry context, that's this one here. So you can design your 3D geometry or your volumetrics, and if you're not that adept in Houdini yet, you might export them to another software package, render them there, animate there. Turns out that even if you're focusing on one context, you're immediately confronted with this. So this is the list of nodes, of operators, as they're called, in the geometry context. They are shitload. They don't even fill the screen. But the thing to understand here is, this is a bit like this. It's a diagram of an engine, yes, but it's so convoluted and so full of intricate details that you actually don't need to know to understand the working principle of a 4-stroke engine. And it's the principle that counts and that you need to understand. So, for example, in this 4-stroke engine, it all breaks down to these 4 phases of combustion and exhaustion. So the key takeaway here is try to get your mental model right. Not necessarily focus on the intricacies first. You will have time to do that later. So, with that in mind, let's become VEXtremists. What a pun! And the basis to becoming good at VEX, or to start learning VEX, is again finding the underlying principle. And when finding the underlying principle, I want to talk about 2 stories that relate to finding a principle, because VEX in essence is a given code. And there are some famous examples of code, and I want to talk about 2 of them. The one is code in the 18th and 19th century. So this guy is a Frenchman called Jean-François Champollion. I think that's how you pronounce him. And at the end of the 18th, beginning of the 19th century, there was this ancient Egyptian craze happening in Europe. Because in the end of the 18th century, the French invaded Egypt and were discovering all these treasures in the pharaohs' tombs. And they were taking them back to mainland Europe. So occupying yourself with ancient Egypt became really fashionable in those days. Yet there was this one missing piece with ancient Egypt that no one had figured out yet, and it's these weird symbols that appeared everywhere, the hieroglyphs. And no one could read them. There was no idea about what they actually meant, how they worked, no clue, and it was bugging people. And then, at a certain point, one of Napoleon's army's soldiers found this piece here. And this, of course, is the Rosetta Stone. It's a rather drab-looking stone, I think about this high. And it's got an inscription in it. And you can see a part of the hieroglyphs up here. This is another, at the time, totally obscure language called Old Aramaic. And at the bottom, there was a 3rd language, Ancient Greek. And people could read Ancient Greek. So the French got very intrigued in this. They were like, oh, maybe we can use this to decipher the thing. So let's take it back. And of course, what happened is the British invaded Egypt. And so the French were like, yeah, let's leave the stone here. We make copies of it, but let's run. And the British found the stone. And they were like, this is intriguing. Let's take it back home. And it actually resides in a museum here in London. You can see it. So they took it back. And meanwhile, the race to decipher the hieroglyphs was on. And it took some years to actually decipher them. But in 1822, this guy actually had a breakthrough. So he used the old Greek text in combination with the old Aramaic to decipher the hieroglyphs. And the key to deciphering them was figuring out that the hieroglyphs could mean different things. They could mean words on the one hand, they could mean letters on the other hand. And the key takeaway for this, and the solution for this code, was that there was actually a text with the same meaning, the same content, written in 3 different languages. So that's one of those 2 examples that I want to give you, and it's quite known. The other one centers around this man, Bill Tutt, a British man, and he made quite an interesting discovery in 1941. And the story is not only about this guy, but also about an unknown German lazy radio operator guy. And it starts in 1940. And who has heard of the Enigma? Some of you? Okay, good. The Enigma is well known. This is not about the Enigma. Enigma was the coding device used by the Germans to communicate with their submarines. And they were like, yeah, this is somewhat safe, but we are not too sure about it. If it is highly safe. We need something more secure for communications that goes to the German high command and to Hitler directly. And they invented this beast, the Lorenz machine, which was an electromechanical thingy that you hooked up to a teletype, so a typewriter that typed over phone line or over radio line. And this thing was secure. In theory, this thing should have been not decryptable in the 1940s. However, there was this one thing happening. When in the 1940s, in 1940, the Germans introduced this thing in the field. They had this, this radio connection between Athens and I think it was southern Europe somewhere. And an operator started encrypting a message, typing a message, a few thousand characters. And so he typed away this message, and the receiving operator received the message and was like, no, I didn't get it, please repeat. So that was when the sending operator got really fed up. And instead of changing the code, he used the same coding settings, hammered away the same message again, but this time he was also lazy, not only sloppy, and he abbreviated words. So the British, of course, intercepted both messages, and early on ended up with 2 texts, slightly different, encoded with the same code, meaning the same thing. And it took the British only a year, without even having seen this machine or having known any intricacies of this machine, on the one hand, to figure out the code, to rebuild a working replica of the machine, and to read the German encrypted messages in nearly real time. And the key, of course, was having 2 slightly different texts with the same meaning, encoded with the same key. Which leads me to code breaking Houdini. What is our lazy German radio operator here? What is our Rosetta Stone when trying to break into VEX? It hides in this image, and by hiding I mean it's in plain sight. These guys here are Ken Thompson and Dennis Ritchie, and they've been working in Bell Labs in the 60s, and Bell Labs in the 60s was a bit like Google nowadays. It was where most of the technical innovation came from in computer sciences. And those guys not only invented Unix, which iOS I think is still based on, the standing guy here invented a rather obscure language called B, in an effort to provide a possibility to develop operating systems, which was really a challenge then, because computers were getting fast, but programming operating systems was really a chore using assembler and very low-level tools. So he invented B. And Ritchie took the same language and developed it further and called it C. And you might have heard of that. C turned out to be extremely popular. It made it very easy and very accessible, or rather easy and accessible, to develop operating systems and develop code in general. So why is this vintage language of interest to us? Well, it turns out VEX is something that we call C-like. And in contrary, and we can discuss this, in contrary to what most people think, in our case, at least when learning, this is kind of a useful thing. So break out your beards, cigarettes, and bell-bottoms, and we're going to program like it's 1972. The useful thing about VEX and C is that all of these languages here are C-like as well. And although we are working on a course on VEX, on an introduction, we haven't finished it yet. So your most likely route to learning VEX is learning one of these languages first, or at least the basis of the languages. And what we like to recommend here is processing. You see it in a screenshot in the backdrop here. And it's a Java-like, a C-like language that's catering to visual artists, to designers, and allows you to develop mainly 2D, a bit of 3D simulation and animation as well. And it has the same syntax, the same structure as C, and thus the same structure as Java and as VEX. I recommend this guy here. It's the Coding Train by Daniel Schiffman. He's got quite a quirky style of teaching, but I recommend this as a quick intro into processing. He's got a whole playlist, Introduction into Processing, where he goes over Computer Science 101. So this is one part. You have the structure of your language. Now, what do you need to talk to Houdini in this language? This is the one single most helpful page in Houdini's help there is at all, period. It's the list of VEX functions. So you now understand the structure of a language. You now need the words to tell Houdini what to do. And what functions are, they are just calls made to Houdini to tell Houdini to do something. And they differ slightly. They differ from processing to Java to PHP to whatever. And this is the full list of commands that's available to you in Houdini, in VEX. And this is where it gets really interesting and really useful, because it turns out you can use VEX in many areas in Houdini.
VEX in Houdini is sort of a lingua franca, meaning that if you know VEX, you can basically use the whole application without concentrating on these different contexts. I personally have the history of starting out with Softimage, then moving to Maya, then using a little bit of 3D Studio Max, and for a long time Cinema 4D. Then I switched back to XSI because of ICE back in the day, and then I started using Houdini. So for me, it was very hard to then be faced with all these different contexts and understanding what this program wants from me. So my way into Houdini was through VEX. I learned VEX first and then used VEX throughout the application. And I want to show to you how the knowledge of VEX helps you a lot, because then you can concentrate on just one thing instead of learning everything. I have a very simple example here, and this is a fall-off example. What I just do here is I take the distance between 2 points and then I remap this range to serve as a fall-off value. Basically, this is what happens. So this purple circle here is my fall-off, and the white dots represent points, and if I have a point at the center of the circle, I have a fall-off of 1. So full fall-off. If the point happens to sit on the diameter of the circle, the fall-off is 0. And in between, the fall-off is interpolated, and I have 0.5. Outside of the circle, the fall-off should be 0. And now I want to show you how I can apply this to the entirety of Houdini. The first example is from SOPs. I can use this fall-off to take some points and color the underlying sphere with the fall-off to create this raspberry, basically. So what I have here is I create a sphere, and then I just scatter some influence points on the sphere, and I animated this value here, and so I have more and more points being scattered on the sphere. And then I put down a point wrangle and put some code in the point wrangle. I show the code in detail later on. And this gives me a nice fall-off that I put in CD. So I have this nice fall-off behavior on the surface of the sphere, and if I scatter more points, I of course get more fall-offs. So this is the code I used. It's a lot of stuff, of course, but basically what I do here is just this. So this is the 2 lines I showed you earlier. I create a distance with a distance function, and then I refit it to generate my fall-off. Next example. I can do exactly the same thing, but using volumes. So in this setup, I just create a box, and then I derive a volume from that box, call it density, to be able to easily set it in the volume wrangle. And then I do an ISO offset to have another volume to scatter my influence points. And then inside of the wrangle, I have pretty much the same code as before, but this time creating density instead of color on the surface. So I have exactly the same thing in my volume using VEX without the necessity to figure out how all this works. All I have to understand is what data is it that I'm working with, and then I use my VEX function. And here I have the code again. Looks a little bit different because I'm dealing with many input points now. That's why I'm having this loop. But it boils down to using exactly the same code again. So no different operators, just the same thing.
Oh, thank you. By the way, calling the contents of a volume density is one of those standards I've been talking about.
Yeah,
You can call it anything, but density is one of those standards for scalar volumes.
Call it density. So why not apply this to DOPs? In this setup, I built just a little grid of boxes. I just copy the boxes over to the grid and have this packed grid of boxes, transform them up, and then put them into a DOP net. And before I do that, I want to create an influence point. So I create with an add sub just 1 point and animate it to move through my grid of boxes. I do this copy with a sphere just to visualize the fall-off. And you see it's traveling through the grid of boxes. And inside of the DOPNet, I have just a standard RBD setup with an RBD solver set to bullet. And I have a RBD packed object, so standard behavior, what you expect from the shelf tool. But this time, I extended the setup with a geometry wrangle. And as soon as I put down the geometry wrangle, I have my place where I could put my VEX code, and I'm exactly in the same location as I have been before in Subland. And if I do that, I can use the fall-off to scale my rigid bodies. And because I'm in DOPs now, they react to my scaling of the fall-off. Very useful effect. And I mastered DOPs without having any clue about DOPs whatsoever. But it does not stop here. So this is the code from the DOP network. And again, it's just these 2 lines that do the stuff. The rest is getting data, setting data. It does not stop here. We have a context that is very scary to most of you. I assume, at least it was scary to me. It's called chops. And in chops, it's exactly the same thing. What I do here is I have a box and a sphere, and I use a sphere to serve as a fall-off. And if I move the box, the chop net is driving the scaling parameter, and I'm using the sphere as a fall-off, basically, so as an influence object. And I wired this up. Here I just show that I can use VEX to do a wireframe behavior in the viewport if I set a detail attribute. And inside of the chop net, I just import the properties of the box and the sphere, and I use again a wrangle to make this work with pretty much the same fall-off code that I used before. Now mastering chops. Here is the code, and this is a section that is exactly the same as before. And the last example is the shading context. The nice thing about Houdini is that I can program my own shaders using VEX. And in the shading context, it's exactly the same thing. I have a sphere here, and I scatter some points on the sphere, like in the SOP example, but this time I write them out to disk, because Mantra on render time has no clue about the Houdini scene, so it needs to read the data from disk. So I quickly save it out as a BGO file, makes the sphere visible again, and then I created this material. And inside of materials, you can use visual programming with nodes, but you can use a snippet node, and that enables you to use exactly the same VEX code as everywhere else in Houdini. And this gives me, with the same code, the same fall-off again. And now that I coded this up, I can go into my code, change the fit range, and have small fall-offs, or change it in the other direction, have large fall-offs. So you see, this is the code for the shader. Again, the same this function and fall-off function. You see, VEX is very, very versatile. It boils down to this. It's basically one function, and you only have to understand this one function, which in my case is a fall-off, but can be a lot more complicated if you like. And then you have get data and set data. So the only thing you have to understand about Houdini is how to get your data from the application, how to put your data back. And that was different in all these different examples. But the core function is always the same.
And that part, the getting data and setting data, is the Rosetta Stone part of Houdini.
Exactly.
We make it sound easy, but we actually ran into exactly the same problem while I was in Romania, and it took me, I think, 4 hours to figure it out, how to actually, the syntax, it was just like, I was cursing.
But nevertheless, it's, this get data and set data part is the essence of understanding Houdini context. And VEX, at least to me, makes it so much easier because you're directly confronted with the data. It's not something obscure that's running through wires connecting nodes, but it is there in front of your eyes, and this VEX functions page helped me a lot in understanding what type of data is it that I'm dealing with and what am I supposed to do with it. That's what I want to take away from here.
Yeah, basically what you're doing is you're bypassing lots of the Houdini user interface to be able to just code in a language or design in a language that you know. I just want to give you 3 other examples that I hope will communicate the power that lies within VEX. And what we're using here is a cell noise, in this case in 3D, and how cell noise works is this. This here is what we've been talking about. This is a function call in Houdini, and it just tells Houdini, please calculate the cell noise and output the results into these 2 variables, f1 and f2. And what a cell noise is, at each, you scatter points in your space, and at each point you sample how is the distance to the closest point and how much is the distance to the second closest points. And that's what's been written down into f1, distance to closest point, and f2, distance to second closest points. And the second line here is you just subtract those distances and check if they fall underneath a given threshold. In essence, is what you're doing is you check if they become the same. So if a point if any position has the same distance to both points. And if it has so, again, in our case, in a volume, we're just setting a value to 1. And you can do that, of course, in the material context, as Manuel has shown. So again, these are this is the setting, and this is the function call, and you end up with something like this. This might not look spectacular. Put it into a bump or a normal map, tweak it a bit, add some noises, and you end up with a really nice leather shader, a procedural leather shader, for example. You can also use a thing in COPS that is a 2D compositing environment. And this is where VEX was really crucial in a project we've been doing like a few months ago, where I suddenly had to write some code to output 2D images, or to create something to output a 3D image with calculations. And I could have done it in another language, but it would have cost me forever. So I was like, adapt in VEX, and I was like, yeah, okay, let's try this in Houdini. And COPS was driving me mad because I've never worked with it. The nodes were so arcane to me, I just didn't get the concept. Until I find this one weird node that allowed me to finally, again, drop down a VEX snippet, in this case, again, with the if statement, and here is the function call. And in our case, we end up with a 2D texture, 2D image of a cell structure, which you could render out and then use in another app as a texture, for example. But here comes a really powerful part of VEX. There's this one thing in Houdini called volume procedurals. And what they allow you to do, and it's the same image that I've shown you previously, is Mantra, the built-in render engine in Houdini, allows you at render time to evaluate volumes. Let that sink in. What it means is you can take a really, really coarse volume that does not take much time to calculate, that does not take away much RAM on your machine, and at render time, Mantra, for every array it shoots, it will evaluate a function what value is in this volume. So I will be able to increase the resolution of my volume, increase the details on my volume, without previously having to schlep a giant volume through my scene. This is pretty unspectacular, just to prove the point. Again, same code here and there. It gets really interesting when you have, for example, 3D fractals like this Mandelbulb. And thanks to a guy called Thomas Dottey, who pointed me to this in the comment section on Vimeo. Really helped me a lot in understanding what volume procedurals are. And this here is an extremely coarse volume you wouldn't be able to get the detail out of the volume resolution. I think it's 30 by 30 by 30 voxels, so it's just like a giant blob. But here, I put down the same code that generates my Mandelbulb in my setup. And at render time, for each pixel, Mantra evaluates this function and evaluates the value at the volume. So what you end up with, a giant increase in detail without cost while working in the scene. Of course, rendering takes a bit to evaluate this, but then you have the advantage of not having to drag around a giant setup through your scene that slows down your whole workstation. So just to make sure, this is really the power. This is the beautiful thing that Houdini allows. I haven't seen it in any other software, and when you are able to put code into a volume procedural, it's so amazing what it can do. Really a fanboy of it.
Here's another example. It has its downside to approach Houdini from the VEX side of things. I was new to Houdini. I needed some cloth simulation, so I was like, I don't think there is some cloth, because the cloth solver is actually, or was called FEM back in the day, and then there is grains cloth, but grains to me was simulating sand and snow. I had no clue how to do cloth, so I decided to write it on my own. And this is what happened. This is my cloth simulation. It's a nice little cloth simulation. It's just, it has no self-collision or no collisions whatsoever, but it's easy to implement that. It's based on an article of Jamasutra called Verlet integration or Verlet physics, and it was developed by a guy called Jacobson for a computer game called Hitman to actually solve ragdoll physics, I think. It's a very nice approach. Normally, if you do particle systems, and this cloth model is a particle systems, you do Euler integration. And with Euler integration, you have two variables on every particle. You have the position and you have the velocity. And the velocity is coming from acceleration. By Newton's law, we know that acceleration is basically the force if mass is 1. So you have the force times the time step gives velocity, and then you multiply by the time step again, and you get the new position. That is how Euler integration works, and it's totally fine, it's fast, it's not very precise, but it's good for most purposes. The POP solver works like this, and there is a microsolver in DOPS that has this behavior just built in. But the problem with this is if you want to put constraints into the system, because if you want to say this particle has to be there, you not only have to update the position, but you have to care about the velocity vector. So this guy, Jacobson, thought about what if I can come up with an integration scheme that treats velocity implicitly, meaning it stores the velocity internally. And he came up with Verlet integration, or Mr. Verlet came up with integration. He used it by not storing the velocity vector, but storing the old position and approximating the velocity by just subtracting the old and new positions from each other. That means if I, with Verlet integration, move a point to a certain position, the system automatically calculates the correct velocity. That means if I want to implement constraints with the Verlet integration scheme, all I have to do is just to put the points where I want to have them. And that is very, very easy. That's why I used this for my cloth simulation. And here's how I build it. You see, it's just wrangles. It's using Houdini as an operating system. I put down a grid, and then I divided the grid to form triangles, because I saw this in Maya, basically. It's easier for a cloth simulation to run if you have these diagonal connections. But this is polygons. So it's primitives connecting many points, and I needed some sort of constraints. So I wanted to replace all these polygons by little sticks. That's why I put down this delete sub and get rid of all the polygons, and then I wrote a little operator that just connects every dot with every other dot, using the connectivity information from the original grid on input port 2. After that, I have a lot of sticks. But because of the multi-threaded nature of VEX, I get double connections, because every point of point A is connecting with point B, and point B is finding point A. So I have double connections. So I thought about how to get rid of these double connections. So I came up with a solution to just go over all the connections and write their IDs to a string attribute. So the connection that connects A to B has 21, 24. And the other one has 24, 21. And then I can sort, and with the VEX function, I can find the doubles and just remove them. So after I do that, I get rid of half the primitives, and I'm left with only one connection connecting every 2 points. That's basically exactly what happens inside of the grain source node. If you have a look at this digital asset and go inside, you see that the same thing is coded up there. Then I have to set up some variables for the Verlet integration, especially the rest lengths. It's very important because I want to tell these sticks how long they should be. So I just get the points, A and B, of the primitive, and calculate the distance between the 2 points and use this as the Verlet rest length and set it here. And the last thing I do with another wrangle is to set the constraint type to stick, because in theory you can implement all the constraints you like. Pin constraints and rotational constraints, but I stick with stick constraints. And then back to the other side. I did not get to the idea that side effects used for their grain solver to simulate this constraint network directly. But I was still using wire solvers, and so I simulate the original piece of geometry, and I use the constraints on the second input of the solver as a constraint network, which is not very elegant, but it works. Inside of the solver, which is just a SOP solver, I have the geometry coming in, and on the very first frame, I switch to the input 1 node, meaning I read the default values. And after that, I use the input from the purple node, which gives me the last values from the last frame. And the very first thing I do there is to accumulate all forces. So I just sum up all the forces. In my case here, it's just a hard-coded gravity. And then comes the Verlet integration. And this is a beautiful thing. This little wrangle here, with just one line of code, basically, other than getting data and setting data, is the whole integration scheme. So this is Verlet integration. And after that, I have to care about the constraints. And how these constraints work is I want to converge to the right result by iterating. This is called Jacobi iteration, and I just do setting the constraints over and over again. So with this node here, I read in the constraint geometry, I look up where the particles should be, I put them there, and then I iterate. And I do this as long as the whole solution converges to a stable result. That is, again, exactly what the grain solver is doing. It's just that when I wrote this, I had no idea about the grain solver. That's why I wrote it myself. Let me quickly show it to you. Here, you see that I really, for the constraints to work, I do nothing but setting the position. So it works like this. You have 2 particles, and they are a certain distance apart. But then you have the rest length attribute, and this rest length attribute tells the particles to be further apart. That is the target state. So what I do is basically I take this rest length, move the rest length between the 2 particles, and then I'm able to calculate displacement vectors, because I know where the particles are at the moment, and I know where I want to have my particles. And then I just move the particles over with P is P plus my displacement vector. And after that, I have the particles where I want them to be, and the new length is the rest length. Now the next set of the next constraint comes in the loop, and it might happen that this constraint again moves the positions of my particles, but as I do this 200 times, it shakes into a usable result. And after this for loop, it's a SOP level for loop, I have a class simulation. That's all that is to implement a class simulation. And when I did this, one of the first things I did with VEX in Houdini, I was really excited that Houdini gives me an environment to code stuff up that easily. Doing this in processing, doing it in pure C or Python really takes a lot of effort. But doing it in Houdini is not only very, very fast to implement, but extremely fast to execute. So you actually can use this in production, although it's just everything added together, 30 lines of code or something. And
yeah, I think you
doable for me.
I think you quickly mentioned that, and he just mentioned it. But think about this: VEX, when running in points, is fully multi-threaded. So in theory, when you are doing at least not totally messed up code, it will really efficiently use the power of your machines, and sometimes for simple tasks even more efficiently than some built-in nodes. So that is really extremely powerful.
But although I used this in production, this is not how it is meant to be. And after discovering the grain solver, I now use a grain solver because it's just implemented more smartly than this stuff. But nevertheless, good to know that you can do it on your own. So at iXponsor, we are doing motion graphics, a lot of motion graphics for Nike. And I want to show you some stuff we did for Nike. Last year we did the Presto project, which was very funny. It was a lot of work, but it was fun to do it. And this is the movie that came out. As you can see, thank you. A lot of transition effects, and that was actually the part where the shield is or where the shoe is transforming into the shield is the part I wrote this fluid simulation, or this cloth simulation for. The initial briefing was, well, we have this Presto shoe, and now we have a new one meant for winter times. And it's stronger, and it protects you, and it's reflective, and please show this in a movie. So we usually start with playing around. We do shitloads of layouts. These are some of them, just that you see the process at Exponsa. We do just try out different stuff. How can we submerge the shoe in an ice block and still see through the ice block that the shoe is protected against environmental influences? Then we tried stuff out to make to visualize how the shoe is reflective and can be seen at night. And of course, we worked on the shield transform.
And usually what we do in layouting, this is, I'm not sure if this is special, but some people mentioned that this is special to our sponsor, to how we work. We usually in layout phase, we already work in full 3D. So we usually refrain from using lots of Photoshops or lots of compositing. We try to solve everything in our 3D software package, so we are sure we can produce the stuff later on.
Although this is slower than doing it 2D or faking, it later on pays off because you just have setups that you actually can create. So here you have layouts regarding the shield process and then the ice growth. And I talked about the growth solver behind this ice growth on FMX this year, I think. So many layouts, and Nike looks at the layouts and then has a lot of comments, and then the next round we'll alter the layouts. And before we go into production, we normally create up to, I don't know, 500 layouts, I think. But then it converges to something. And here we thought about how we can show that the new shoe has a new outsole. Because the thread of the new outsole was deeper, because it was meant for winter times, and the surfaces in winter are slippery, so they deepened the thread, and we thought about how to show this in the movie, actually. And the final solution was to just show a morph from the old outsole to the new outsole. And I want to show you how I created this morph in Houdini. So the problem with this whole thing is I had, to start, I had two outsoles with different topology. This is one of them, and there I have a second one. And they are similar, but not identical. And eventually I want to morph between the two outsoles. That means I need, if I'm not relying on VDBs to do the morph, I have to have the same topology for both. And that's a problem. So I have to think about how can I create two outsoles that have different properties, but the same topology. And that's why I modeled this cage geometry here. I had the idea to take a cage geometry and then basically shrink wrap it to the outsole models to have the same topology on model A and model B. What I do here is using the connectivity sub to get a class attribute and then split everything apart so that I have individual parts, because it's oftentimes more easy to work with individual parts. Once the stuff is working on one part, I can just apply it to the other parts. And then I do a remesh of one of the parts, giving me a very dense mesh of triangles. that I can use to work with. The whole idea is basically inspired by ZBrush, where you have this reprojection workflow. If you have a model with different topology, you can go into ZBrush and just reproject it to a high resolution model. And that is basically what inspired me to do this in Houdini. Now that I have this hull here subdivided, I wrote a little shrink wrapping solver. So that's basically a solver that's built around a Laplacian smooth. The smooth node in Houdini is not fast enough for this purpose. It's not smoothing enough. So I wrote a little VEX smooth node that's using Laplacian smooth and really smoothes this stuff by a lot. And I repeat this smooth over and over again, and then I use a VDB from polygons to generate a volume. And inside of the solver, I use another VOP to check if the points already lie inside of the target volume. So it just smoothes the stuff until the surface collides with the original outsole. That is what actually happens, giving me the effect of a shrink wrap. I rendered this out for you to see. It's hard to see because the soles are so similar, but if you look at the top left corner of the movie that's showing in a second, you see the differences. So that is basically the output from the solver. The solver is just taking the stuff and then shrinking it down onto the original model, giving me two models of the same topology that are very similar to the original result. But it's not enough, because this solver is stopping before the result is perfect. Here you see the differences between the outsoles. The red parts are the parts where the stuff actually collided with the original model. But what I now have is I have a very good starting point for the next operation, and the next operation is a ray operation. I just want to ray this stuff to the original outsole. But the problem with these outsoles is that they are convex forms, so they have a lot of valleys and cavities and stuff. So with this starting point, it's a lot easier to ray this stuff down. And again, I rewrote the ray SOP here in VEX, just because I want to ray in two directions and pick the better one, just because of these valleys. And although it works quite well, you have areas where it's not perfect. Sometimes it picks the wrong direction, and you have these little dark spots here. So it's not perfect either, but we are getting closer. And the last step is then again a loop where I just do the Laplacian smooth again, and then after every smoothing step, reproject the result using the volume gradient and the volume sample to the surface. So I just smear the stuff along the surface until it sits. And this gives, if I make the node active here, the black spots will disappear in a second. You see, and now I have pretty much a perfect fitting of the new topology to the old outsole. And if I do this with both models, I end up with two nice representations of my two outsoles showing the exact same topology. That is what I got here in the end. And then it's just a matter of loading the geometry in and using VEX to blend between the two. For this, I coded a little 3D gradient, and for this gradient, I used exactly the fall-off I showed you earlier. So I created a line in 3D, and I used this line to define a three-dimensional gradient using the dot product. And if I move the line through space, you can see this here, it generates the gradient on the outsole. And I use this gradient as a value to blend between the two outsoles. So if I move this, the gradient updates in the transition area of the gradient. I just introduced a little bit of noise to make it look a little bit more natural. And then I have this point wrangle down there. And this point wrangle is just one statement. It says add p is add p times weight, plus up input 1p, so the other outsole, times the reciprocal of weight. And this gives the blend. So if I use this wrangle with my fall-off value, I now can blend between the two outsoles, and I can go very close, as this is not faking, but it's a real thing. It's totally perfect. I can perfectly do the blend. And I can even, after this, what was not necessary for the original setup, use an attribute transfer to steal the normals from the original models to make it look just perfect. I then introduced some noise for the transition area, just to make it visually a little bit more interesting, and that was the final shot for the movie. You see, even in production, a lot of VEX. But that's not necessary. It's my personal preference. For me, it's just easier to type something into a wrangle than to search this large convolute of nodes for the right node to do the right thing. If you're working with Houdini for years, that's probably different. For your viewing pleasure, a little development reel of stuff we did for this press conference.
Which already brings us to our conclusion here. And admittedly, it might be a bit daunting, but we gave you hints. So if you want to go into VEX, it's important to find your proper Rosetta Stone, so your proper way in. Not everything might work for you personally, but or at least my way into VEX was via processing, so that's one hint. Then it is daunting, so don't let yourself get too frustrated. It is like solving a Sudoku. You will run into troubles, you will run into problems, you might have to start over, but it's also extremely rewarding and it's extremely powerful. It's maybe the single most powerful skill you can acquire in Houdini because there's so many places where you can use it. So before we go to questions, I think we have very little time left. Just a hint, we are on Patreon now for some weeks, and yes, we are planning on doing an introduction to VEX, so you might want to consider supporting us there. And yeah, that is it. Thanks for bearing with us. If you've got questions, please feel free to ask them. And thanks for having us and staying with us.
Thank you.
So any questions? We got this throwy if you want to debate us on anything.
Please, one question. I want to throw this one time, at least.
Anyone?
Is this on? Yeah. I just wanted to know, when you're, so the two different outsole models that you've got, so when you're like sort of just basically shrink wrapping it, that's all live code. That's all been sort of reassessed at render time. So when you're doing the transition between the two, it's actually going through those loops at the same time, or are you baking them off?
No, I'm baking everything out. It's too slow to do it live. No, I'm just preparing the two outsoles. That's a beautiful thing, and then I write it out as BGO, and that's real time. So it's basically a machine to shrink wrap stuff, and you can encapsulate this away into a digital asset and use it later on because it's always the same thing. So if you need to wrap topology A to topology B, I do a lot of 3D scanning, photogrammetry scanning. It's extremely useful to have it there, for example, because there you do a retopo model, and then you want to have all the detail from the high resolution scan. So it's basically exactly the same process. I just recreated basically what ZBrush is doing with its reprojection function, more or less. But nice that it's possible to do this in Houdini directly. Another $800 saved. Anybody?
Anyone? Okay. Ben, thanks
So
so
thanks
much.
a lot.